I am Viswajit, and this is joint work with Kirtavasan and Barnabas, other folks from CMU. And today I'm going to talk about using random scalarizations for multi-objective Bayesian optimization. So a quick overview on what Bayesian optimization is. So in Bayesian optimization, we have an unknown function f that we wish to maximize. And the only way we get information about this unknown function f is by choosing a point x and getting some noisy observed value fx. So single objective Bayesian optimization has been used in a lot of applications using hyperparameter tuning, experiment design, online advertisement, and scientific discovery. However, in certain applications, we are encountered with multiple objectives that we need to optimize, and often they are competing in nature. For instance, consider the drug discovery example. So suppose we want to discover a drug that has huge potency to cure some disease, and it has minimum side effects or minimum toxicity, and we also want to maximize the solubility. And often these objectives are conflicting in nature. So some drug that is extremely useful for some particular disease might have very severe side effects. Such problems also exist in finance, machine learning, and also manufacturing. So consider this simple multi-objective optimization problem. So suppose we have two objectives, f1x and f2x. So increasing values of f1x denotes decreasing toxicity, and increasing values of f2x denotes increasing potency. And we see that, and the green region denotes the set of possible values of f1x and f2x. And we see that we cannot decrease the toxicity and increase the potency at the same time. Because if we could do that, we would have a point around here, which is not, this plot is showing that it's not possible. So now consider any point inside the feasible region, this point denoted by 1. So for any point inside the feasible region, we can find another point 2 that is better than 1 in both of the objectives. On the other hand, if you choose a point on the boundary of this feasible region, if you improve one of the objectives, the other objective has to get worse. So in other words, the points on the Pareto front, on the boundary of this feasible region, they cannot be improved in both of the objectives simultaneously. So such points are also known as Pareto optimal, and the whole set of such points is known as the Pareto front. So the standard goal in multi-objective Bayesian optimization is to approximate the Pareto front using a set of points, which is shown here using blue circles. And there has been a lot of work in this regard, and some of the prominent ones have been shown here. In this paper, however, our goal is to locally approximate the Pareto front without utilizing a lot of resources to estimate the other parts of the Pareto front. This is useful because in some cases, the user might want to explore only certain parts. For instance, in the drug discovery example, the user might want to only explore the drugs that have a small amount of toxicity and try to optimize the potency only in that region. Also, in other instances, users may not be interested in extreme values of the objectives. So there has been some prior work in this regard in the lines of constraint Bayesian optimization and preference-based optimization. We, however, used a random scalarizations approach. So random scalarizations have been previously used in other works, but mostly to explore the whole Pareto front instead of some certain parts. And we also generalize this approach to more general scalarizations. And we show that it leads to an intuitive set of algorithms that are flexible and general, have theoretical guarantees, and are computationally cheap. So what are scalarizations? So scalarization is any function that produces a scalar value from k objective values. So a simple example is a linear combination of all the objective values. And lambda 1 and lambda 2 here have to be positive. And we denote by x star lambda as the maximizer of the scalarization function. Now, for all positive lambda, one can show that x star lambda is Pareto optimal. So you choose the lambda, you get a point on the Pareto front. Choose a different lambda, you get another point, and so on. Now, suppose you have a prior over lambda. So this variable x star lambda is now a random variable, and this in turn imposes a probability distribution on the Pareto front. So the probability distribution is shown using the dotted lines, and the samples are shown using the blue circles. And so this is the core idea behind our approach. So the user chooses the scalarization function and the prior distribution, and this is how he controls which region to sample from. Now, before we go into the algorithm, let us take a quick overview of what Bayesian optimization algorithms look like. So in the single objective case, we initialize with an empty observation set, and then we repeat the following for t iterations. In the first step, we compute the posterior of the true function given the current observations. So the true function is assumed to be sampled from a Gaussian process, and so we can also, so depending on the observations, we can compute some posterior. So in this plot, the true function is shown using the blue curve, and the posterior is shown using the red dotted lines and the gray envelope. So the red dotted lines denote the mean of the posterior, and the gray envelope denotes the point-wise variances at each point. Next, we optimize an acquisition function, which depends on the posterior to get the next candidate point xt. And we evaluate the function at xt, and we update our observation set, and we keep repeating this until t iterations. And then we return the maximizer of the posterior mean. One can also return the maximum of the observed values, or there are multiple variants of this. So in a similar vein, we propose the following algorithm for our approach. So we start with the initial set of observations initialized to the empty set, and we repeat the following for t iterations. In the first step, we sample a weight vector lambda from the prior, and we compute the posterior of each of the k objectives independently, given the current set of observations. And then we compute an acquisition function that depends on the sampled vector lambda. This was not in the case for single objective optimization, but it's in the case of the multi-objective case. And optimizing the acquisition function, we get the next candidate point xt, and we observe a noisy value yt at point xt, and we add it to the observed data set. So this function returns all the points x1 till xt, and also all the values y1 to yt. And we hope that that will approximate the interesting region of the Pareto front. So it turns out that the acquisition function can be simply taken to be a scalarization of the single objective acquisition functions for each of the objectives. And although I am explaining this using very simple scalarization, like using the linear scalarization and only two objectives, it can be generalized to a much general class of scalarizations. The details are in the paper, and you can take a look if you are interested. And we also show that this algorithm actually works by showing that the regret goes to 0. And we will take a look at this result later in the slides. So to test the effectiveness of our algorithm, we perform some experiments. The first one is a synthetic experiments. So we have two synthetic objectives, f1x and f2x. So the gray region in each of the plots denotes the feasible region of the problem, of the objectives. And the blue points denote the values sampled by the algorithm in the early iterations, and the green points denote the values sampled by the algorithms in the later iterations after it has learned the functions well. So we use three priors. The first is denoted by mid, the second is denoted by top mid, and the last is denoted by flat. So the first prior is designed to sample from the middle part of the Pareto front. And we see that once the algorithm has explored enough and learned the functions, it is successfully sampling from the middle part of the Pareto front. In the second one, it is designed to sample from the top and the middle parts of the Pareto front. And we see that even in this case, it's sampling from the desired regions. In the third one, we sample the weights from a flat distribution. So ideally, it should give us, so it should explore the whole Pareto front, which is also the case here. But this kind of evaluating the performance of the algorithm by visualizing only works for two objectives. But for evaluating it for more number of objectives, we need to come up with some sort of metric. So this brings us to the regret. So we define a base regret till step t, denoted by RBT. I won't go into the details of the regret, but in brief, the regret is designed so that it has a small regret if the sample points cover most of the probability mass of the imposed density. On the other hand, if it can incur high regret in one of these three cases. So in the first case, the points are all Pareto optimal, but they do not cover a lot of the probability mass. In the second case, they are Pareto optimal again, but it doesn't cover, it's not even in the region of interest. So it will again incur a high regret. In the third case, it is neither Pareto optimal nor near the region of interest. So we prove a theoretical result on this, and we show that as the number of steps goes to infinity, the regret goes to 0. So we prove this by showing that the cumulative regret grows sublinearly and the base regret is less than or equal to 1 by t times the cumulative regret. So I'll skip all the details, but this is the basic result, that the regret goes to 0 as t goes to infinity. So now we test this on a relatively higher dimensional problem. So we want to optimize locality sensitive hashing, which is used for approximate nearest neighbors. And our goal is to minimize the memory, maximize the accuracy, and minimize the query time. And this plot shows the regret values of our proposed approach and all the other baselines as well. So our methods are shown using the green and red lines, and we see that it achieves a lower regret compared to the other algorithms, which are designed to explore the whole of the Pareto front. So as a conclusion, we proposed a multi-objective Bayesian optimization algorithm, which is based on random scalarizations and helps us explore only a part of the Pareto front without utilizing resources on approximating the other parts of the Pareto front. And we also show that our algorithm minimizes a notion of regret in the multi-objective setting. And the exact rates of the regret are there in the paper. And we also experimentally demonstrated the effectiveness of our algorithm on both synthetic and real examples. So you can find the implementation and the examples in the Dragonfly Bayesian Optimization library. Thank you.